Section 4.4, Real Zeros of Polynomial Functions. Factor theorem. A polynomial f of x has a factor x minus k if and only if f of k equals 0. So this is saying if your polynomial has a factor of x minus k, so some linear factor, leading coefficient 1, then you will have no remainder. Or you have no remainder when you substitute in k, only when your polynomial had this linear factor. All right, exercise 1. Use the graph of f of x and the factor theorem to list the factors of f of x. Well, the factor theorem says that a polynomial f of x has factors x minus k if and only if f of k equals 0. So if we can find the places where f of k equals 0, then we'll know that we have the factor x minus k. Well, f of k or f of x is just your y value. So where my y values equal 0 are on my x-axis. So that seems to be the point x equals -3, or we can think f of -3 equals 0. So by the factor theorem, this implies that x minus -3 is a factor, or x plus 3 is a factor. I also have one here which is pretty close to -1/2. So f of -0.5 or -1/2, however you want to write it. I'm going to use the fraction is equal to 0. So this implies that x minus -1/2 is a factor, or x plus 1/2. And the last time I see my y's being 0 is at x equals 2. So this implies x minus 2 is a factor. So the factors of f of x are x plus 3, x plus 1/2, and x minus 2. Multiplicity. Consider the function g of x equals x minus 2 to the power 3 times x plus 1 to the power 2. This function has factors x minus 2 and x plus 1 with zeros. Well, my k would have been 2, and here my k would have been -1. Notice that the factor which gave me my 0 of 2 was power 3. So my 0, 2, has multiplicity 3, and my 0, -1, came from a factor that was power 2, so this has multiplicity of 2. I can find the degree of g of x by adding up all my multiplicities. So the degree of g is going to be 5. This is the graph of g of x. So notice right here, this is the value x equals -1, which was one of my zeros. And right here is the value x equals 2, which is my other 0. At -1, my graph just touches the x-axis. And at 2, my graph crosses the x-axis, but it kind of flattens out before it crosses. So it's like shallow, not a very steep crossing. What we know is that at a 0 of even multiplicity, the graph does not cross the x-axis. So when we had even multiplicity of 2 at x equals -1, notice we just touch the x-axis. So we just touch. At a 0 of odd multiplicity, like what I have at x equals 2, where I have 3, which is odd, the graph does cross the x-axis. And the higher the multiplicity, the more the graph levels off near 0, which is why when my multiplicity was 3, I kind of flattened out before I crossed. So I'm going to level off more if my multiplicity is higher. Complete factored form. Suppose a polynomial f of x has n real zeros, and these real zeros are called c sub 1, c sub 2, c sub 3, all the way up to c sub n, where a distinct zero is listed as many times as its multiplicity. So above, where we had like multiplicity 3, I would have just written out 2 3 times. Then f of x can be written in what we call complete factored form, as f of x equals a sub n, your leading coefficient, times x minus your first zero, times x minus your second zero, times x minus your third zero, all the way up through x minus your nth zero. Exercise 2. Write the complete factorization of f of x equals 5x cubed minus 5x squared minus 20x plus 20 with zeros, -2, 1, and 2. Well, if these are all of our zeros, this is our c sub 1, c sub 2, c sub 3, and our leading coefficient is 5. So a sub n equals 5, c sub 1 equals -2, c sub 2 equals 1, c sub 3 equals 2. So according to my formula above, I can write f of x as 5 times x minus -2 times x minus 1 times x minus 2, and simplifying, I get 5 times x plus 2, x minus 1, and x minus 2. If you multiply this out, you should get back the same polynomial you have above. Exercise 3. One of the zeros of the polynomial h of x equals -2x cubed minus 6x squared plus 2x plus 6 is 1. Express h of x in complete factored form. If one of our zeros is 1, then this implies that x minus 1 is a factor. If I divide my polynomial by this factor, it'll help me continue to factor my polynomial because it should lower the degree, and then I can try to factor what I'll be left with, which will be quadratic. And since I'm dividing by a linear polynomial with leading coefficient 1, I can use synthetic division. So my k is 1. My coefficients are -2, -6, 2, and 6. Notice I don't need any placeholders and it's already in descending order. So let's do our synthetic division. Bring down the 2, I get -2. I multiply by 1, I still have -2. -6 plus -2 is -8. Multiply by 1, it's still -8. 2 plus -8 is -6. -6 times 1 is -6. 6 plus -6 is 0. We expected to get a remainder of 0 because it told us that this was a factor. And if it's a factor, we should not have a remainder. Okay, so what this says is I can now factor my original polynomial as the one I divided by times the polynomial I just found, which is -2x to power 2. Remember, you need to drop down a power, minus 8x minus 6. And now I want to try to factor this polynomial. Well, this is quadratic, and we have some tricks to help us factor quadratics. The first thing I notice is that I have a common factor in this red polynomial, and that greatest common factor is -2. So I'm going to factor that out. If I factor that out, what I'm left with is x squared plus 4x plus 3. And now I don't want to lose any of the factors I've already accounted for, so I'm kind of going to write this in a new order, but I'm going to put that x minus 1 at the end so I don't forget about him. So now I have this negative 2 that I factored out, and I want to try to factor this quadratic in red. Well, two numbers that multiply to 3 but add to 4 are 3 and 1. So I can write this as x plus 3 and x plus 1. And now I have the complete factored form of f of x. Notice my leading coefficient stayed the same. I'm supposed to have the same a sub n, which was negative 2. And then I just have x minus, or it looks like plus, but think of it like minus a negative, each of my zeros. Some of you may have noticed that the original polynomial was factorable, and you didn't have to even do this synthetic division. This synthetic division is very helpful when you're having a hard time seeing your factoring. So if you don't notice right away how you should factor your polynomial, or maybe it's too difficult to factor, if you know one of your zeros, you can use synthetic division to try to simplify the polynomial you're looking at. But if at the very beginning you can already tell how to factor it, you can just start factoring. So we haven't talked about this type of factoring, but you may have seen it in a different course. Here we can use something called factoring by grouping. So factoring by grouping, you look at two groups of your terms, and then you factor each of those groups. So in my first group here, the greatest common factor is negative 2x squared. When I factor out negative 2x squared from these first two terms, I'm just left with x plus 3. For my last two terms, the greatest common factor is a positive 2, and when I factor that out, I'm left with x plus 3. Now, terms are separated by plus or minus signs. If things are being multiplied together, you can think of it as the same term. So since I have this negative 2x squared times this factor, I'm going to think of this as a term, and same idea here, this as a term. When I look at these terms, they have an x plus 3 in common. So I can factor out the x plus 3. When I take away the x plus 3 from this first term, I'm only left with this negative 2x squared. And when I take away the x plus 3 from this second term, I'm only left with the positive 2. Now it still doesn't quite look like this one because I would have to keep factoring. This is actually a pretty involved factoring problem, so this method over here might be easier. But now let's factor this second polynomial. So I see that I can take out the negative 2. And what that's going to leave me with is x squared. If I take negative 2 away from positive 2, it's going to leave me with negative 1. And remember, I still have that x plus 3. And maybe you recognize this as something called the difference of two squares, which factors as a plus b and a minus b. So I do get back the same factorization that I got here. I just did all of it without even knowing that one of my zeros was 1. Problem 4. Write the complete factored form of the fifth degree polynomial f of x shown in the graph. Assume that all zeros are integers and that the leading coefficient is negative 1. So for complete factored form, we have to know where our zeros are. And remember, zeros happen when y equals 0, or where you touch or cross the x-axis. So I have a 0 here at x equals negative 2. Notice it only touches the x-axis, which implies that this has an even multiplicity. I have another 0 right here at x equals 1, and it crosses the x-axis, so that implies that I have an odd multiplicity. Also notice though that when I cross at 1, again, it does that thing where it kind of levels off, where it kind of flattens out. So that implies that I'm going to have a higher multiplicity. I usually use this arrow to mean implies. Okay, so you should be able to look at your graph and identify these types of ideas. I also know that I have a 5th degree polynomial, and when I add up my multiplicities, I should get back the same degree as my polynomial. In addition to that, I'm told that my leading coefficient is -1. I know my zeros are -2 as well as 1. And now I just need to figure out what the multiplicity is or what their powers are. Well, if the degree of this polynomial is 5, at the -2 I need to be even. I could either be a 2 or a 4. But at 1 I need to be odd, and I should have a higher multiplicity. If this is a 2, then this would be a 3. If this was a 4, this would be a 1, because again it has to add up to 5. But this should have a higher multiplicity because it levels off. So I'm pretty sure that leaves me with the complete factored form of -1 times x plus 2 to power 2, because it's even, and x minus 1 to power 3 because it's odd and should have a higher multiplicity.